This is, it's a real pleasure for me to have a chance to introduce Daniel Severino. He's here because we invited him to teach us about this mode of galaxy formation, which is called cold-flow accretion. Is exactly what he's going to describe now. For reasons that I'm not going to detail, we are interested, very much interested from an observational point of view in this mode of accretion. And I don't know whether I should say this, but I was trying to find someone that could kind of illustrate us on the physical properties of these cold flows, in particular if they are observed at low redshift. And he is one among the worldwide experts in the field. So he was in all the papers here and there. And it was after glancing at many papers that I figured out that he was Spanish and he was working in Madrid. So it was a big surprise. I'm very happy that he's here. So just, I'm going to finish just saying that he did his PhD under the supervision of Clipping in New Mexico, in the US, and then he moved to work with Deckel, which is kind of the father of this business of the cold-flow accretion in Jerusalem. And now he's in Madrid with
Juan de la Cierva.
So, it's your time.
Okay, thank you. So, hi everyone. Can you hear me? Is the thing working? Good. So, let us thank Jorge for the invitation and the opportunity to be here and present this talk. I'm going to talk about the cold flow accretion in galaxies and the consequence for galaxy formation. So, first, we'll give some introduction to the cold mode and hot mode picture. And then I will focus on two different topics that are very biased towards my own research. So one is the consequence of this cold flow accretion for the formation of high redshift galaxies, these clumpy galaxies at high redshift. And then I'm going to talk about the detectability of the cold streams as Lyman limit system or Lyman alpha blocks. So first, let's start with the classical picture of galaxy formation that was laid out several decades ago. So the main ideas, the main hints of galaxy formation were already there. So they start with a gas and dark matter accretion into a halo. So the material is flowing to the center of a potential well, gravitational potential well. But the gas has some pressure, so it's shock heated to high temperatures. That's the typical idea. So the gas is heated to the virial temperature, roughly, and then start to cool and lose the thermal support, but the angular momentum is preserved. So the material sinks to the center and form a disk at the center. In the disk, at some point, it's achieved high densities, so they can form stars. Those stars, especially the most massive ones, explode after some time as supernova explosions. So they deliver material, energy, and momentum back to the system in a kind of feedback loop. So now we are going to test all these ideas using modern techniques. So we are going to check all these assumptions behind all these kind of processes. And this is what now modern computers are telling us about the distribution of gas inside the matter halos. So this is the gas distribution. The points are the stars. So we see first a galaxy at the center, so that's good, at least. This is our cosmological simulation with galaxy formation, cooling star formation and feedback. Just say that. But we see that the distribution in the halo is not uniform. The gas is flowing along these three streams, so they deliver a lot of material all the way to the center of the halo. So the material is coming from the cosmic web at very large scales all the way to the center. And at the center, we have what we call messy region, very complicated interface between the streams and the galaxy. This is something we still don't understand. This is where the angular momentum of the streams is redistributed into the angular momentum of the galaxy. Okay, yes, I didn't say this is about redshift 2. And this is like a massive galaxy, 10 to the 12 at redshift 2. I will go to lower redshift later. So this is one of the situations. So, okay, what happened with the shock front? Do we see an accretion shock in the simulation? The answer is yes. This is one example. This is just a slice through one of these cosmological simulations. The temperature is shown here in the colors. So this center in the galaxy, so this is a small black dot here is the disk Ejon. Again, this is about redshift 2, because we can see this phenomena. So the redshift, we see the material. Okay, the arrows are the velocity field. So we see here in this corner high velocity and cold material. So this material is flowing to the center of the halo. And this is the accretion shock. You see after the shock, the material is now much hotter, like 1,000,000 degrees, but the velocity are much lower. So here most of the kinetic energy is being transformed into thermal energy. This is the accretion shock. The most important point, is that this accretion shock is only stable under some circumstances. Only if the rate at which the gas at this temperature cools, only if that rate is lower than the rate at which the gas can be compressed, only in that case the shock is stable. Otherwise, it's losing the pressure support very fast and the system cannot react to that. And this is what is happening down there. So here we see cold material and high velocities all the way to very close to 10% of the virial radius. So here, what's going on here is the density along these streams is much higher than the density here. So the gas is cooling very fast, so fast that the accretion shock is unstable. So it cannot develop, and the material is flowing directly to the center. This is the idea of cold streams. So in this seminal paper by Wimmer and Deckel, they talk about this shock heating scale. So this was just one-dimensional simulation of like accretion of concentric spheres of gas. So you can go from high and low redshift, and if the temperature of the halo is much lower than 1,000,000 degrees, meaning between 10 to the 5 or 10 to the 4 degrees, that's roughly the peak of the cooling curve. So the cooling is so fast that the shock is unstable. So we have the cold mode accretion. The material is being accreted to the galaxy without being shock heated to high temperatures. But we are going to now to a very massive halo with a virial temperature much higher than 1,000,000 degrees. Then the shock is stable. We are in the regime of hot mode accretion. That's the typical two modes of accretion. But actually, there is a third mode of accretion that is going on. So this is the same, the virial mass of the halo function of redshift. So especially at high redshift and massive halos, the picture I showed before, we have the situation that we have these narrow streams of dense gas. So in those streams, the cooling is very fast, and we have cold material penetrating inside the hot corona. So this is cold into hot medium. And at low redshift, we have basically all cold or all hot. So we have two different histories. If you have one halo which is growing, but has very low mass, high redshift, it's always this cold mode accretion. And now if the halo crosses that boundary, this shock scale at low redshift, it has a typical halo mass of like M star, or the projected mass of at that redshift. In that case, the gas is almost symmetric, and passing this boundary means that it's going to be heated to high temperatures, just because the virial temperature is now hot enough, so cooling is not so efficient. On the other side, we have another halo, it's more massive one, so that one here is crossing that transition scale at higher redshifts. So now we are talking about 10 to the 12 solar mass halo at the redshift 3. In that case, we have those cold streams, and it's called into hot regime. So that's basically, this regime here is very important for the star formation at a high redshift, basically redshift 2 or 3. So here we can see the difference between high and low redshift. So it's the same, again, from different simulation. So it's the same mass scale, 2 times 10 to the 12 solar masses, but there are two different halos at two different redshifts. So if we are talking about high redshift, here showing the reacted density, this one, you see, density of the gas is distributed in those narrow streams, very dense filaments, which are cold. You can see the temperature here is around 10 to the 4 degrees. So those are the cold narrow streams, a high redshift. Now at low redshift, that's more typical halo, 2 times 10 to the 12. So now the filaments, as you can see, are much thicker, like comparable to the virial radius of the galaxy. So the accretion is done more spherically. They are not much different in the density, so there are no cold streams. And we see the temperature is all dominated by the hot accretion. This is what we are learning from this picture. Yes. Yes. Okay, so this is a different. This is a slice and this is projected. So you don't see the same clamp. So you don't see this clamp here. Maybe you can see this one. So these clamps are going to be much colder. Depends on the density. Sure. Mm-hmm. Definitely. Yeah, we are talking about the bottom of the cooling curve, basically, and that so the is called in the sense of collision ionization. So if there are no source of ionization, photons or something, gas at that temperature cannot be collision ionized. So it's all neutral, 10 to the 4. We are going to 20,000 degrees, then you see a collision ionization. That's the collision ionization. So Keres et al. Showed that this transition mass is not a sharp transition. The hot material is being built over time. Okay. So if you focus at redshift 0, here I'm showing the gas fraction on the cold gas or the black points, and the hot fraction is this red curve. So for redshift 0, we see if we are going to very small halos, like lower than 10 to 11, almost all the material in the halo is cold. And on the other side, we are going to very high masses. Almost all the gas is hot. But you always see some residual of cold material. And that's going to be very important for the overall accretion of gas to the center of the galaxy. This is what is most important now, because this is what is going to fuel star formation. So what they're doing here, they are now using a cosmological simulation with it's a large box with many halos, very poor resolution, but they can stack different profiles. So they're taking all the profiles of the halos in that range, around 10 to the 12 solar masses at redshift 0. And then, so these different properties, they divide the gas into cold mode and hot mode. So the blue regions are the material that was never shock heated to high temperature. And the hot mode is the material that was, at some point, went through an accretion shock. So we can focus just here on the gas accretion rate. So there we can see the cold mode is in blue, the hot mode is in red. And you see the total is dominated by the cold mode accretion. Why? Because even if the gas fraction in the cold phase is low, they have much higher velocities. So they dominate the overall accretion from the virial radius all the way to 10% of the virial radius. And that one predicts one accretion rate of like 1 solar mass per year for that kind of mass scale. Again, if we go to much higher redshift 2, we see much higher accretion, like now it's like 10 times higher, and also it's much flatter. So here we can say that 50% of the material that reach the virial radius end up at 10% of the virial radius. Something very similar to what we are finding in our simulations. So what's going on here, even if we have this hot corona, we have always, if we have enough resolution, we see these cold streams. This is shown in this picture by Oscar Aguet. It's a bit complicated because blue means density, so those are the narrow streams, which deliver most of the material to the center of the galaxy, which is at the center. The red is the temperature, so this is the hot corona. When you see those streams penetrate to the center of the halo. And the green is the metallicity. So that's why it's important to have very high resolution. Can we switch on the lights, please? I'm going to show us an animation of one of my simulations. It's much better to see. It's only going to be a few minutes. So we are using the zoom-in technique. So this whole region, this is just a small fraction of the whole volume. That the whole region is going to collapse into a single halo by redshift 1. You can see a high redshift is a complicated web of filaments. The stars are the white dots. You can see that everything is coming through the streams. Those are the incoming mergers that are going to merge with the central object, but smooth gas in color and the stars are going always along the streams. This is what we predict for hierarchical clustering. This is what we always see this kind of structure. This is the cosmic web. This is the main galaxy at the center, the main halo. Now we're going to see a closer view of another animation. So here we're going to see the formation of a big galaxy at the center, which is being fed by 3 streams. And we have enough resolution to resolve the streams like 2 or 3 substreams. But high redshift, everything looks like a cosmic web. At the node of the cosmic web, you see the first galaxies forming. They give you some bubbles. This is explosion due to supernova feedback that produce those outflows, high redshift. You see sometimes. The main galaxy is going to form here at the center. And you can see another bubble here. So we are now going to see the streams edge on and then face on, because the 3 streams are actually in a plane. You see some shocks there due to sometimes are just video shocks, sometimes just shocks due to supernova explosions. So this is one of the streams. See, it's very thick, but it's broken into 3 substreams. So they leave material to the center. Now we are going to see the stream edge on. So this will give you a high signal in the H1 absorption, for example, because it's going through a lot of coal and neutral gas. So this is the main galaxy at the center, and this is one of the streams. This is the second one. This is the third one. This is the same picture we saw before. Now having a merger, you can see the accretion shock moving onwards. But the material is flowing always along these 3 filaments. It's okay, thank you. On the light. Okay, so now I'm going to talk about the consequence of these cold streams for the formation at high redshift. And this violent instability. So we see galaxies at high redshift which are very perturbed, very disturbed. These kind of galaxies are seeing the red frame UV. See, they are broken into those giant clumps, which are giant H2 regions. And if now we look at the same galaxies in the red frame visible, we also see a stellar concentration at the center. So we also see a bulge in this kind of perturbed systems. Actually, they are perturbed systems, but when they look at the gas kinematics, most of these massive ones are rotating. They are rotating thick and turbulent disks, like was shown here. This is the kinematic map from H alpha, showing this rotation pattern. So now there are several studies of this kind of clumpy fragmented disk. They were also called chain galaxies or cluster galaxies. And now here we see these clumps in the red frame UV and H alpha, but you can also see in the H bands. They're actually real features that we need to understand. So here in Dekker and Severino, we put together a very simple toy model, and then we have also simulation that confirm this scenario. So this simple model has a disk of stars and gas, and at the center we have a stellar bulge. The disk is being fed by a smooth stream that keeps a very high surface density, so high that the disk is unstable. Went through a Thumre instability, so it formed those giant clamps. These giant clamps start to move inside the disk, so they're forming the disk and then start to rotate, start orbit around the center, so they drive turbulence into the medium. At the same time, the turbulence dissipates on some dynamical time scale. Thus produce a steady state, so the system is kept in a quasi-unstable situation with Thumre parametric unity of roughly, but those clamps are losing angular momentum and energy because of those interactions. So they move to the center. They migrate to the center until they coalesce with the central bulge. So this is one channel to feed a central spheroid. The other traditional channel, more classical scenario of bulge formation are through mergers. So the same streams are also clampy. They carry galaxies in it. So when the galaxies merge with the center, they also contribute to the growth of the spheroid. So we are going to concentrate on this scenario. Just few numbers. So this is just very simple. We are talking about the Thumre instability in a cosmological context. So everything depends on the Thumre parameter, which is, as mentioned, a parameter takes into account three processes. First, we have the surface density. The big sigma is just the gravity try to collapse a patch of the gas in the disk. But we have two processes that try to counterbalance the gravity. One is the shear of the flow, because that patch of gas is living in a differentially rotating disk. And also we have pressure, velocity dispersion of the gas. So those two things compensate to Q about 1. But if the surface density of the gas is very high, the radius of these clamps are very big, like could be 1 kiloparsec. So we are talking about these giant clamps. So in this self-regulation state, the key parameter is what we call the disk fraction. It's the fraction of material inside the disk compared with the total amount of mass inside the same radius, the radius of the disk. So if that parameter is like 1/3, so 1/3 of the mass is in the disk, that simple toy model predicts roughly each clamp is forming in 2% of the mass of the disk. We sum up all the clamps, we are talking about 20% of the whole disk. It's a small fraction, but that's enough to keep this regulation state for several gigayears. It's a steady state that's very stable. We call it violent disk instability because everything happens on dynamical timescale. Just the dissipation of energy from the clamps and the interaction of the clamps are happening on dynamical timescale, and after a few orbital periods, the clamps merge with the center, and that migration timescale is comparable to the star formation timescale. So we are talking about dissipative coalescence of the clamps. So that's why we can produce a compact spheroid at the center. And this is what we see in the simulations. It was shown in Deckensal and Severino. You see the same qualitative picture. This is the gas surface density phase on. So we see very perturbed disk. So this is rotated in this direction. So we see these giant clamps, some elongated features because sometimes shear is more important and disrupt some features. But we see the same qualitative kind of mass and size that we were expecting from the simple toy model. Roughly at the same time, a different group using a different code, they found roughly the same thing. So this is a very robust feature by now, the stability. So what we are doing now, we are building a sample of simulations. We have now like 70 simulations with different viral masses. So each one follow the formation and evolution of a single object. We have between 10 to the 11 solar mass halos to 5 10 to the 12 solar mass at each one, with a resolution between 15 and 70 parsec. I'm not going to enter into many details of this ART code, AMR code with gas cooling, star formation, and feedback. A nice property of this code is that we don't have any free parameters in this model. All the coefficients we have are constrained by stellar evolution, the amount of supernova explosion and the amount of energy in the supernova that we have, the properties of the ISM, and the Kenikal-Smith relation. So that all the coefficients are constrained. We are not playing with the parameters to get some kind of result. Actually, I saw those clamps well before Avishai told me that he has this kind of toy model for clamp formation. So this is what we see in a wildly unstable clamp. So you see it's going very slow, so you can follow one of these clamps as they migrate to the center. So the material is coming here from the stream. They hit the disk here, so they always deliver material to the outer disk. So the clamps are forming here in the outer part and then migrate to the center. You can see after 2 or 3 orbital periods, they migrate to the center. And new clamps are forming, so this whole stationary process can be stable for several gigayears. After a while, the gas fraction is low enough or the bulge is too big and the stability stops. You see at the very end. But you always see formation of clamps. One is forming here, one is forming there, one is going to coalesce right now to the center. This is the density of the gas. So at the very end, we can see only one clamp forming here, and there are those elongated shear features because this thing is much more massive. So we're not going to see the stars. These are the stars younger than 100 million years. Just to compare with Res frame UV. This is one of the simulations, Payson and Young, and this one, two typical galaxies from the UDF. Just to show you that we have the same clamping morphology. The qualitative properties are very similar. But now if we look to all the stars, so this is just stellar surface density, we see at the center of the same galaxy a massive bulge. So this is an efficient mechanism to build a bulge at the center. That's sometimes difficult to observe. So now we are building a sample of simulation at H1.3. This is a subsample, the whole thing we have now. Just to see, this is again the stellar surface density. So this is the distribution A-Young. So we see some clear disks. Sometimes it's more like a spheroid. The more typical case is like something like that. It's more elliptical shape. So this could be like a fast rotator, elliptical. Because they will see this component. And now we are comparing with observations around redshift 1.5. So this is the Shen et al. Relation for early type galaxies. And people found that at high redshift, those galaxies are much more compact. This is the sample from the Desmosaurus. The galaxies are much below the redshift 0 line. And our simulations are roughly there. So roughly consistent with the mass size relation. At least they are in the ballpark in the right place. We still don't produce many of these ultra compact galaxies with size lower than 1 kiloparsec. It could be just because the selection in this sample we don't have smaller halos or smaller galaxies. We also don't see any of these very extended objects, so we are somewhere in between. So now we can take one of these simulations and then we can select different stellar components based on the kinematics of the stars. So we are taking the material with high angular momentum. We see the contribution from a thin disk. On the other side, we take the material with very low angular momentum. We see an spheroid, the same galaxy, just 3 different components. And actually, on the average, 70% of the stars are actually in the spheroidal component. And now we're taking a Cerseic fit and see, okay, what kind of properties we see in this spheroid, which is built by binding this stability. So this spheroid is compact, but it's also a classic spheroid. It's a Cerseic index between 4 and 5. Because this clamp migration is so violent, happening on few orbital periods, it's not a circular, slow process. It's always very fast. So that produces a classical spheroid. So this is pretty much a work in progress. We are now going to produce a catalog of mock observations. Actually, those are simulations that went through a post-processing pipeline. It's called Sunrise, which gives you the light at different bands. We are also adding dust. just using the metallicity of the simulation. So we see here so this is the same galaxy at two different redshifts. See some dust lanes. Blue is the red-free UV, so this is a very high star-forming galaxy. See a lot of clumps, very violent. This is going through this VDI phase. And the same galaxy at redshift 1.1, you see this has a much redder color, much more quiet, doesn't have much star formation, have this kind of elliptical shape. And the point that there are no mergers about 1 to 20 involved between those two snapshots. This is all violent instability at work, which build this kind of compact spheroid. On other simulation, we also have merger, but during this period, we didn't have any kind of merger. So we can see, okay, the growth of the spheroid between those 2 points were driven by the instability itself. So now I'm going to change topics. I'm going to talk about the detectability of the cold streams. So one of the best way to detect these cold streams are through quasar absorption lines. So just imagine that we have these cold streams, but in the background we see a bright quasar, so we can take the spectrum of that quasar and see what kind of absorption lines we see at the redshift of that galaxy. And decide, okay, what kind of properties of the gas we see for that stream. And to make that kind of predictions, we need, okay, in high resolutions, we need to resolve the densities of this stream. We need to know the temperature of the streams, but we need to know the ionization fraction in the stream, of what kind of ionization structure we have, and the metallicity if we want to study metal lines. So that's tricky. So that was the first step we did in 2010. Just we're using tables from Cloudy to see the effect of the ionization. So this was a HALO redshift 0.5. I think, and here we see only the column density of the total gas, total hydrogen. So we see a hot diffuse corona, disk at the center, and those stream in green. But now if we include this Cloudy table, we compute only the H1 column density, you see that the diffuse corona is gone, it's all ionized. The disk is also very strong absorber, but we see a lot of absorption of that streams. And little squares were the line of sight with detection in magnesium 2, one of these typical absorbers at the redshift. So we see that the streams have a H1 column density between 10 to the 18th, 10 to 19 at the redshift. So we went a step further. We now include relative transfer, post-processing, because now we are taking into account not just the cosmological UV background at a redshift, but also the stellar sources, the UV photons produced by the galaxy itself, and what's the effect of those photons in the area around the galaxy. And we found this was very important. Also, was very important to add, because we didn't have relative transfer at running time, it was all done post-processing, so we mimic relative transfer using a very simple model for gas self-shielding. So if the gas in the stream has a density higher than a given threshold, we assume that the gas is self-shielded. So there are no UV photons, not many UV photons hitting that piece of gas. That was also very, very important piece of physics. And we found different large range of simulations that these cold streams are detected as Lyman limit system with low metallicity, like 1% solar metallicity. This is what you can see here. The streams are in blue, green, and red. Red is like DLAs, so it's basically the galaxy and the satellites, and blue is more extended 10 to the 17 HALO. So that was done in Fumagalli 2011. Now in 2013, we are studying the covering fraction of those Lyman limit systems. So it's the covering fraction inside the virial radius, because there are some observations that we can compare with. This is the covering fraction as fraction of the HALO mass. The circles are the simulations. So we found about 20% of covering fraction within the HALO. That's consistent with some some observations, or is statistically consistent with those observations of Lyman-Break galaxies. It's consistent with our first crude models in Cohort et al. 2012, where we just took a table from Cloudy, giving very similar covering fraction. But the point is now, this point is very much inconsistent with the simulation. This is the sample from Prochaska 2013. So those are quasar-selected halos. So here in the sample, we have a pair of quasars. So a quasar in the background, they shining through the gas of another halo, hosting a quasar. So we are talking about massive galaxies, 3 times 10 to the 12. In that case, the covering fraction they observe is very high, like 60% of all the region around the Vira radius was covered by cold gas, and we are getting much lower here. So this could be a problem of the simulations. Maybe we don't have enough outflows to produce this high volume with cold gas, or could be just a selection effect of the sample. Because there's something quasar selected, so maybe the same mechanisms that fuel the central quasar also keep a very large fraction of cold gas in the halo. So we still don't know. So the final thing I'm going to discuss is the detectability of cold streams as Lyman alpha blobs. We are talking about Lyman alpha emission because that's the typical line we expect from this kind of streams, because the temperature in the streams is between 10,000 and 30,000 degrees. Those are roughly the peak of the Lyman alpha emission. So in this paper, we just integrate, we compute the emissivity of Lyman alpha in each cell in the simulation, and then we integrate it and get some estimated surface brightness. And this is one of the examples. Then we smooth it to given filter just to compare with this kind of Lyman alpha blobs. Those are large structure at high redshift, could be like 50, 100 kiloparsec across. So cannot be single galaxy. They're very extended. And we are proposing that those are actually the detection of cold streams at high redshift. Again, in this paper, we didn't have relative transfer, and that's a crucial thing for Lyman alpha because it's a resonant line, so it's scattered a lot. So what we're doing now with Dan casing is to use relative transfer calculation to compute the amount of Lyman alpha coming from the halos. I think that's my conclusions. So the stability of the gas accretion shock depends on the gas properties, basically the cooling time versus compression time. The cold streams can efficiently feed massive galaxies at high redshift. These high redshift gravitational unstable disks break into clamps that migrate to the center. So the final products of this instability are compact and classical spheroid or spheros. And finally, the cold streams can be detected as low metallicity Lyman-Levin systems or Lyman alpha blobs. Okay, thanks.
Thank you, Daniel. Time for questions.
You put up a picture where there are clamps that are being formed in the galaxy, and there are clamps that come from along the stream and fall inside.
Yes.
So which of the two processes is dominant in galaxy formation?
I would say that both. We are now studying, like we are dissecting the bulge at the end. So we say, okay, how much material was coming from outside, the ex situ star formation, how much material was in situ star formation. We found like 50, depends on the galaxy, depends on the emerging history, but it's 50%, I would say. So 50% of the material that end up in the spheroid were coming from outside, the 50% were material in the disk.
And if I may, I have another question. Did you say that
Sorry.
At some point in your simulations, you're saying that you're separating components by the angular momentum.
Yes.
Is that a clean division?
No, it was not clean division.
So is it an easy way? Is it easy to do? Because I suspect it's not.
In observations or in...
Well, in your simulations.
Dime?
In your simulations.
In the simulation is easy because...
Because phase space I would expect to be fairly smooth in general.
Yeah, what we're doing...
So where do you draw the lines? That's my...
Yeah, what we are doing here is to compute the angular momentum of the whole galaxy, and then we we compute the ratio of the angular momentum of each stellar particle with the maximum angular momentum of that particular galaxy, that particular star. So if the material has angular momentum close to the maximum angular momentum, is here in the disk. So we are collapsing. We are only moving in the direction of the angular momentum.
Yeah, but the division is not sharp.
Yes, of course, it's not sharp. That's why we have something in between. But if you see the histograms of this normalized angular momentum, you see always a strong peak around unity. A lot of material here are moving in circular orbits, very similar to circular orbits, very close to circular orbits. Material here are moving in different orbits. So this is big.
At which redshift do the cold streams form?
You see from the movies, they form a very high redshift. So at the same time, one of the first structures to collapse are these pancakes, and then you have these tiny filaments there. Those filaments start to merge with each other. So we can see streams, very smooth streams like a redshift. Depends on the resolution you have. You will see that any redshift, very high resolution, very high redshift.
What is very high for you?
The 6, let's say 6.
Okay, thanks.
Very high, something like that.
The good and the bad things of the simulation is that you may just think of things would maybe wrong. For instance, in the images you have shown, it also seems to appear when you form the central galaxy, there are also things which are clumps, some of which seem to be massive enough to become more galaxies. So it seems that from your simulation, under some conditions, you may also be forming clusters of galaxies. This is one question. I mean, from what
yeah, but depends on the size of the box.
That's right.
Only if we have the long modes, we are going to see the cluster formation. For the first animation, yes, there is one cluster in the full 40 megaparsec box, but we didn't simulate that.
Okay, but this is one thing. And another thing that appears naturally is the spiral structure, which the spiral structure is clear that, and it remains for quite a while, because while you are moving these clumps to the center, you still keep the spiral structure somehow. So I understand that at the end it disappears because you have a massive bulge, elliptical or whatever. But I also suppose that depending on the range of masses you are playing with, you may end with a spiral. Like some dwarf galaxies do have a spiral structure that maybe can be understood with this mechanism. So is this?
Yeah, I was showing most of the galaxies are massive already redshift 1. We are talking about 10 to 11. So we expect those galaxies to be spheroid by redshift 1. So now we are extending the sample to much lower masses. Depending on lower masses, that things like feedback are very important, much important than this scale. So that's why we now have a new model of feedback, trying to keep the fraction of stars low, as we expect, low efficiency of star formation. And the idea is to have these galaxies. Yes, and we see some of this. But these galaxies, a high redshift, are also very perturbed. They're not seeing this.
Yeah. So related to Jesus' question, so in these spheroids you see, where does all the angular momentum go? I mean, you're saying these clumps are coming down through the disk. There's a redistribution of the stars, and then you end up with a spheroid. Mm-hmm. But where is the angular momentum?
Yeah, some angular momentum goes to the smooth disk. You see, we have very extended disk, like 10 kiloparsecs. Mm-hmm. So that's a lot of angular momentum goes to that gas. A lot of angular momentum goes to the dark matter, actually. So the dark matter is like a sink of angular momentum. It originally doesn't rotate, but in isolated simulations, you see that, for example, the formation of a bar drives a lot of angular momentum. So it's the dark matter halo which takes that angular momentum, which you can see kind of dark bar rotating.
So if you were to plot the angular momentum as a function of radius for one of these spheroids, forget the disks, but the spheroids, what would you see? You would see a transition, would you expect to see some rotation signature at very large radius? Or, I mean, what would you predict? I mean, is there some way of measuring this angular momentum? That's my point, at larger radius.
If I combine the whole thing, I didn't do it for the spheroid itself. If I do it for the whole galaxy, you see the component of high angular momentum from this galaxy. So we see high rotation. So we're consistent with a fast rotator, which we consider. And that rotation dies out at large scale. That's something very different what you expect from a merger. In a merger, there's a lot of orbital energy, angular momentum, so a lot of material is actually stay with high angular momentum.
Yeah.
In this case, we don't see that.
Okay.
I have two questions about the detailed simulation of a cold stream feeding a disk. One is the metallicity of the clamps that are formed by accretion, and the second, which is related, is what would happen if this, I understand that this stream has an angular momentum which is kind of aligned with the angular momentum which was already present in the disk. What happens if it is kind of perpendicular?
No, actually not really. This is what we're expecting too. So if we compute the plane of the streams and then the plane of the disk, and is completely misaligned.
Okay, so in this case,
in that messy region, there's a lot of redistribution of angular momentum, which is something that we still don't understand.
Okay. And about the metallicity of the clamps?
Yes, the metallicity of the clamps formed inside the disk
that are fed by the stream.
Okay, the first one, when they form at the beginning, they have low metallicity, but you can see as they migrate to the center, they are getting enriched. So they have higher, close to the disk metallicity, or even higher metallicity than the disk at some point. Because we have self-enrichment of metals in the streams. Yeah, they take like 200, 300 million years to reach the center. So during that time, the supernova explodes inside the clamp and they enrich the material. So something that we don't model very well is the outflows coming from these clamps. That's something that is coming in the new simulation with much stronger feedback that we didn't discuss here. So in that case, there's some outflow that can remove a lot of metal. In this case, they're not.
Any other questions?
Okay. And well, before asking you, let me simply remind that he's going to be around us until tomorrow. So if you want to talk to him, just either tell me or show up by his office. That is the center corridor upstairs, the end. Okay. So, and the question is about supermassive black holes that you hadn't mentioned at all. Yes. So, are they present in these simulations? No.
We don't include, not at this moment. So, at some point, because you see that we produce a massive spheroid, so we expect a massive black hole at the center, and because we are talking about gas accretion to the center of the disk, they can also feed a massive black hole. So, the idea is to at some point include the AGN feedback into the simulation. Be one in the to-do list.
Okay, I think we can thank Daniel again. And remember that there's a scientific coffee in the library at 12:30.